is simple. When you play, say you play chess, play tennis, I don't know, chess boxing, it's a Wu-Tang joke, I guess. Wu-Tang fans in the room? All right, yeah, Staten Island. So, if you play with someone who's a grandmaster at chess, and you play your first couple games of chess, you're going to be, he's going to wipe the floor, right? The floor will be wiped by you, right? If you play with someone who is kind of moderate, well, then you might have a fighting chance. But it turns out, and a lot of cognitive scientists have demonstrated this, if you play with someone that's within your skill level, at any endeavor, that's 10% above or below, there's some threshold, you will advance. So they played each other, and eventually these bots, I guess I'm drawing them bigger as they get better, right? They progressed at the same level, right? They kept learning from each other because they were within a certain range. One time, one bot would win, so it was kind of this thing. This is very similar to a method in reinforcement learning. There's a number of algorithms that are just kind of applied to reinforcement learning. It's not exactly actor critic, but it kind of is. I won't go through the terms in more detail. But the notion is that you have this notion of you have two bots kind of fighting each other. And it kind of simulates, like if you're trying to make a decision in your head, right? There's part of you that wants to do something, the part of you kind of comes against it. And then after a while, the answer you come to, I don't know if it's the best decision in the world, right? Because who knows? But at least it had a few chances of being iterated through and thought through, right? Yeah.
So as two noobs, are they prone to explore almost exclusively and have nothing to exploit, and that explains why they...
Yeah, you're stealing some of the thunder there, but yes, there is some of that. So, and that gets into some of the other things. So I'll move forward. It's a good thing this video doesn't play, but I highly recommend watching this video because it definitely will get your attention. Because I could, joking about this. If you think about this, this machine, these bots became super masters in 3-4 days, right? And the joke, being that think about what they could do, and not so much because they're smarter, because they iterate them, and they operate on timescales just like any computer program in nanoseconds, and so they can run through lifetimes of skill, right? So you heard the 10,000 hour rule, right? Where if you do something for 10,000 hours and you continually, consciously try to improve, you will be a master level. And the example that would be playing the violin, right? Unfortunately, all these other things that we are distracted by humans, right? Fall asleep, eat, all sorts of things in their measure of focus. They don't have that problem, but there's still hope. At least for now. This is an actual, my wife went to Carnegie Mellon, and we were up in Pittsburgh. That's an actual billboard in the middle of town. I added before now to make it a little more promoting. So, there's some math. And a big part of the challenge here is keeping a lot of the formula kind of out of the discussion. Because in 40 minutes, or however much time I have, or 50 minutes, there's only so much, and this really is the hardest class. I can't tell you how many times I hit replay on the lectures, right? Which is another awesome use for online learning, because if you miss something the professor said, depending on the professor, he or she may not be willing to repeat it, and then you have to go through office hours, there's a whole thing to that. But this one was the hardest. You're the second or third person to tell me that, and I don't think more than like a couple thousand people worldwide have taken the class.
I wouldn't be daunted. The real thing that they assume is when you go to do the labs, that somehow you have the ability to express the math right out of your head.
Right, and that is the first iteration of the class. And you can tell, as you're taking this course in edX, like there's a point, about the first third, you can tell somebody's worked through it and kind of like, okay, let's assume. And then the second 2/3, because somebody used to work with, like Wintel, very smart guy. He had done it. He said, oh my God, that's all his class. So I'm doing like the first third, and I'm like, you said that? And then boom, it hit me. It was like, yes, it is the first class. Yeah, question.
Just a comment. I did take the edX data science curriculum last year. And I had a hard time with some of the lectures in there too, some of the math lectures. And I noticed something that really did trick me here, and I don't know if this happened here. but if there's cases where the instructor would be like saying one thing, but pointing at different things. And that, I had to actually go back and replay it and bring my wife in the room and go, okay, she's saying this, but look where she's pointing something different, and that kind of thing, you don't notice it, but when it happens, your brain, like internally,
When you're going back,
your brain internally gets like screwed up or something like that, and it just messes you up. So I don't know if that happened in this class, but sometimes.
No, this was just pure math, and I'll kind of show you some of
That's
that.
hard.
And you can Google it with Bing or use Bing, whatever search engine you like. Microsoft pays my mortgage, so I'll use Bing.
I'll keep it white.
So this is one of the formulae, right? This is a likelihood ratio measure. Look here. It's a triangle, as far as I know. Apparently that means gradient. And I only inferred that because he kept saying, oh, gradient of theta. So it's basically like it's kind of like, how like universities, they have like sororities and fraternities, and they're all Greek letters. Yeah. Imagine if they all had like a big party and then like all the letters exploded everywhere. That's kind of what the formula looked like. But some of them gave me a headache. And like sometimes like, I don't understand it. And I'd be like, I am with Andy in the back. Like, oh my God, I understand the universe now. Like, it's true. So like I would send him a screenshot of this. My God, look at this. This is so beautiful. And then now if I look at it, I'm like, Sarsa, isn't that one of the kids on Game of Thrones? Like, so it kind of leaves you, but so when I wrote about this, it was really hard to kind of keep it within a context that makes sense for developers or software engineers. I'm a software engineer by training and by trade. Now I'm a data scientist, AI guy. So a lot of that kind of, I don't want to say baggage, but I'd say experience, I'm bringing with me. And you'll heard him say, he said something about greedy, and you'll see that word again. Greed's going to come up a couple of times in one of the demos. But let's get it down to the basic elements of reinforcement learning. You have an environment, like a chessboard. You have an agent, right? That's the player in the chess, but not the pieces, right? The state at any given moment is the location of the pieces on the chessboard. Action is any valid action you can make in a given chess. Then what happens is you take an action, the environment changes, based on the updated state, the agent will then receive their own reward based on that, and then the cycle begins again. So an example would be, if I had a chess bot and it was learning, and the first, it would get, and imagining a computer getting a reward, getting punished is kind of a little bit of a suspension of disbelief. You're going to have to bear with me. It'll make sense when you look at the code. But the notion is, what would happen if I had an agent that played a game of chess that would, every time it took out an opposing piece, it would get 5 points. Every time it moved, maybe it costed 1 point, or -1 on the scale. And winning the game, I don't know, I just said, oh, that's a 5. That's going to result in a very aggressive chess play. Yes?
It actually had, so first of all, in chess, there is a standard number that you assign to each piece for the worth of the piece.
Right.
You take that piece. But the problem with that is that if you capture the king, the game is over.
Right.
So that's worth infinite, as a reward or as a punishment.
Right.
And so, historically, one of the problems with chess bots has been they don't take geometry. They don't take the places of the pieces into account as well.
You have to then factor that in. That's incumbent on the engineer.
Yeah.
How you incentivize the bot.
Yeah.
It sounds really weird, right? We're incentivizing a piece of code.
Yeah, I mean, it's just a number you're telling.
It's just a number you're telling it
the
to
bishop
get.
is worth 7 and the queen is worth 10, and the king's worth 100.
But what you're getting in there is this notion, I think it's called the Bellman equation, is the notion of delayed gratification, right? If I attack the queen now, what was the number you gave, 7 or something like that?
Yeah.
But infinite, if I proceed a strategy that will get me towards getting to the king, it's infinite payoffs.
Yeah.
Right? You have a question?
Just curious, Frank. Is this optimization Is that what we're
Ultimately,
after?
it ends up becoming like an optimization.
Okay. All right.
But you have to, it's basically about trial and error.
Okay. Cool.
So, and this is a joke I like to make, is that if you had a self-driving car algorithm that would be incentivizing to do bad things, this is how people learn to drive in the car. And I mentioned self-driving cars because where you find a lot of this is basically they learn by trial and error. And synthetic data is a lot safer. It's a lot safer to push an algorithm. You can see what's going on inside Grand Theft Auto, and no real person gets hurt. But it can do all these sorts of stupid mistakes, and it can learn from that. Another place where you see this is in video game development. We're not so much development, but in people have been taking Mario Brothers and training algorithms and bots to beat Mario Brothers. I think somebody on the Microsoft research team scored a perfect score in Miss Pac-Man. Well, they didn't, their bot did, but it's very interesting in terms of how that works. But really the key here is you have to incentivize properly, or you'll get some unintended consequences. And synthetic data, I mentioned this, is that this is a great way. So you train it on a video game kind of surface at once. No one gets hurt. You can really control the scenarios, right? Like, is it a rainy day? Is it sun in the eye? Is it the sun low in the sky? Is there traffic? Is there, all sorts of things you have a lot more finite control over, rather than just saying, here, go for it. And that makes me wonder, you hear about all these research being done in self-driving cars. They're all done in the Bay Area, which typically has really nice weather. Like, what's going to happen if they get rolled out and, we have snowmageddon, right? How is it going to react, or how is it going to react in the streets of Chicago? But first, I want to talk about the original algorithms. Any biology people here? You know what this is? Chemists? No? It's dopamine, which is a chemical that the brain makes. And basically, it's part of a reward system that biology has produced. And remember, your brain is there to keep you alive. It's not there to make you happy. It's basically there to keep you alive. It's not perfect, because we can see things like drug addiction and how it can kind of hijack the dopamine system. But there's still 7 billion human beings on the planet. I would say net it's a pretty good system. But think about it, if you have kids, about child development, how they learn. Right, so a favorite example is I have a 3-year-old, and he was 2 at the time. My wife and I kept talking about going to the Apple store, right? Because he broke one of the iPads or something, I don't know. But one day I'm in a supermarket parking lot with him, and he goes, "Hey, look, Daddy, the Apple store, Apple store." This is definitely not with the Apple store. And then I look, and if you're familiar with the supermarket chain Latte, right? The O looks like a giant apple. So from his point of view, that was the Apple store.
That's funny.
Right? Or if you have pets, the way they figure things out. Now, if you follow me on Instagram, or you follow my Facebook, or sometimes Twitter, I have 4 dogs. One's a Weimar. Very smart dog. Very mischievous dog. Right? So that is a raw piece of pork loin that she got out. We have a microwave that pulls out like a drawer. She's figured out how to open it, right? And her dopamine hit was getting a whiff of the pork as it was defrosting and basically drinking it open. And that's not like, in the wild would that happen. So dogs and pets, they know who is the person at the breakfast table most likely to give the dog food, right? I didn't teach her. Lord knows she doesn't listen to Nick, right? So you never did, right? So she knows that he's going to. His big brother gave him like 2-3 waffles. She knows he's only going to have 1 or 2. So she's just waiting her turn. Or if he decides that he wants to go play with his trucks, she's just going to scoop it up. Weimaraners are great dogs, but they are not for the first-time dog owner. Look for, if you want some humor, wine crime. Hashtag wine crime on Instagram. Apparently she's not the only one. All right, so we're going to talk about the multi-armed bandit problem. So this term comes from slot machines, which were known as one-armed bandits. So a bank of them would be multi-armed bandits. So imagine a bank of slot machines. Which one of these will pay out the most? You find out. You have to spin them, right? So let's just say the first one pays out at 10%. Now I have a dilemma. I know every 10 pulls I'm going to get a jackpot. Should I bother with the other 4? Because as slot machines go, that's actually pretty good. Should I bother with that? Should I be greedy, right, and exploit the resource that I'm currently aware of? Or should I be curious and explore other resources in the hope that there's a better payoff? And there's a certain threshold there, and we'll actually run through this. So the second one actually pays off at 25%, which, hey, yay me. But then as we go through, we'll see there's kind of a dip. So we know the ground truth, but the algorithm may not necessarily do that. So basically, you have this explore versus exploit, right? If you remember that song, Should I Stay or Should I Go? Right? That's pretty much this algorithm right here. Striking a balance between greed and curiosity. So remember what old Gordon said. Right? Well, it turns out, actually, 5 to 10% of the time, greed actually does work. Because you want to set those numbers, and the experiment is up there. I can share that. It's also going to be, yes, I know. So you just got that. That's funny. All right, so I'm going to pull up. One of the least well-known services we have in the cloud is Azure Notebooks. So how many people here know about Jupyter Notebooks and that kind of thing, right? So if you're not familiar with this, and that is my dog, my kid. All right, so while this is busy loading, basically Jupyter Notebooks is a way that you can interact with code kind of in real time. It's very popular with data scientists because you can do a lot of exploration pretty easily. And I do not like the fact that it's taking that long. Did a lightning strike a data center somewhere? And messing with the,
That's not funny, Frank.
All right,
So it's the demo gods, they do this.
yes, definitely. Ooh, it's bad when Active Directory fails too.
This is a great reason to run your own process of Python locally when you're doing demos.
I think I've drank too much of the top. For 2. All right, looks like plan C is in effect. It's still not even. their notebooks. Let's hope this works. If nothing else, I can at least show you the code that's already run in the notebook. Once the computer likes to play along.
So is it Azure Notebook any different than the Jupyter Notebook, or is it just running in the cloud?
It's basically Jupyter service running on Azure. That's free. That's the big part.
Oh, right.
In the same vein, Jupyter Notebooks and Python is free anyway. So,
All right, let's see what happens. I've not tested this on my local machine, so hey. All right, so I want to show you this here. So if you're not familiar with this, shameless plug, I wrote a really good article. Actually, now that I work for Microsoft, they don't pay me anymore. So, I have an article on kind of the excruciating details on how to get used to this, how to get into Jupyter Notebooks. But basically, how many people here have programmed Python before? Okay, cool. So good number. C#, Java, that type of class of language. This is Python. So basically what I'm doing is I'm importing a couple of important libraries, and I'm saying I have 5 slot machines, right? And I'm going to create a random distribution of numbers. I call that JPs. And that is going to, I plot that out, and I'll show you, these are the payoffs, right? So the first jackpot pays, first slot machine jackpots 54% of the time, second one 27%, the third one 42%, the fourth one at 84%, and the fourth one a little more realistic at under 1%. Right? Any real casino that has slot machines like this would probably not do business with them. So we're going to run that. Oh, it worked. All right, so these are, this is what we know. Now remember, the algorithm's not going to know this. We're just setting up a simulation for the thing to do. And what we're doing is we're going to create here a simulation of how you play a slot machine, right? So you play it, how many machine you want to play, and create a random number. If it's less to or equal to the threshold point, then return 10 points. Otherwise, return a -1, right? So basically, I will let's see. So the new cell. All right, so what I have to do is I have to execute that cell, and then what I'm going to say is I'm going to play machine 3. That's the one that's really good. And remember the third number there. What's the percent chance I'm going to hit a jackpot? Sorry, the fourth one. Yeah. Off. Somebody's walking around one of the speakers with that off by 1 index errors. Joel, yes, sir. Yeah, you have to see it. All right, so I messed up. So yeah, the fourth one in the series, but number. Oh,
that's if you count the zero at one.
Zero with is first.
Yeah.
Yeah. Because this isn't confusing enough. So, so it turns out I won. Game A. Right? Now if I try the last one here, notice how I avoided the number. Just that one. Right? So if I play that one, if I win this one, then definitely play a lottery. Right? So just like anything else in statistics, you just do the same thing a bunch of times and eventually a pattern emerges. Hopefully. Usually. And you'll see that for the fourth machine out of 5, I won most of the time. Index 3, thank you. Index 3, I win pretty much. The last one that has the sub 1% chance of winning, obviously there's none of there. Even if I made that 1,000, one might come up. All right, so now we're going to amp up the game here. We're going to create a multi-armed bandit simulation. And basically what I'm going to do is I'm going to take these as parameters, number of arms, number of iterations we're going to run, and this thing called epsilon, which is a Greek letter, and math people and love weird Greek letters. So I'm going to run this to define it. So what I'm going to do now is I'm going to chart the actual odds, right? Ground truth. Remember, we know this, bot doesn't. And then I'm going to say over 1,000 iterations. So it's basically going to pull the slot machine 1,000 times. It's going to play 1,000 times. Whether or not it pulls the same one or not, we'll see. So what I'm doing here is not only am I going to play the game, but I'm also going to remember what my chances were on that given machine. So let me show you what that does here. Is basically what I'm going to do is run through my iterations and then pick at random. I'm just going to generate a random number, and if that hits the epsilon, if it goes above the epsilon threshold, it's going to exploit. So it's going to pick, and argmax is a function that gets the highest number in a numpy array, right? So if you saw, I kind of zeroed them all out here. So at first I assumed nothing, right? They all have odds of 0 because they have no information. Philosophically, you could debate, should that be 0, should that be something else? We could do that another time. 0 works for a 50-minute session. So what this is going to do is basically, okay, so play the machine. If I don't hit my certain greed threshold, or my epsilon threshold, which basically I'm going to play the ones I've got the best odds on so far. And then what I'm going to do is I'm going to play the machine. I'm either going to get a -1 or 10, and then I'm going to add that information times a bunch of kind of percentage math, and I'm going to store that in what my estimated payout odds are. Right. So remember, estimated payout odds starts off at zeros because we don't know anything, and then each time I play, I'm going to remember. I'm going to store what my odds were on that machine. Then I'm going to go through and basically repeat that, a number of iterations. All clear so far? I realize if you don't know Python, this is not exactly the thing. So what I do now is now I have that, like a test harness. I'm going to plot out what the actual odds are, just because I don't want to have to keep scrolling to the top of the screen, right? And I'm going to say, before I said greed is good 5 to 10% of the time. So this is the optimal number, right? So 10% of the time, it's not going to pull the slot machine that has the best odds on, right? It's going to explore. It's going to play around with stuff, right? And then we're going to show the odds and results of that. And then I'm going to drop it down to 0.01, so it's only going to explore 1% of the time. And this I should call, I don't have a 0, so if this were 0, I'll make this 0. Call that the Gordon Gekko world, right? It's fully greedy.
I don't understand why that's the thing you want to do. I just don't understand it.
What do you mean?
Like, isn't the point of a slot machine always to make the most money possible? So
you got me here. This is a contrived example.
So, but
you're never going to go to a real casino and have 1 in 10% odds.
yeah, but I thought the exercise here was the fact that the 4 or 5 percentages at the beginning, the machine doesn't know at the beginning which one of those is highest.
Right, it's going to learn.
Yeah, so even if it hits the one that's 84%,
right,
the other one might be 90%, right?
Right.
So it has to
explore, and
right.
The exploration I'm doing is just a random look.
Okay.
Right, and then this threshold here, this number here determines how often I'm going to explore.
Yeah.
So that I'm not going to explore at all.
Right.
So when something doesn't explore, it's called greedy. And when it explores all the time, it's going to be exploited.
But how is it greedy?
Explored.
How is it quote unquote greedy if you're stuck at the one that's 20, if you're stuck at the one that's 20% and you're not looking for the one that's 80%.
This is a good point, and the numbers will kind of show off that. Remember, I had the thing in Gordon Gekko. Greed said greed is good. So in this context, greed of about 10% is actually good. Beyond that, it starts being detrimental.
But what about the other thing is
religious and philosophical things aside?
It looked like you had so you're adjusting that number,
right?
And
each one of these
100%.
Right.
If you had it 100%, it would switch no matter what. Sorry.
It would explore no matter what.
It would explore no matter what. 0%, it stays where it is no matter what.
What it's going to do, and you'll see, it'll make a lot more sense when you see the numbers right now. Bear out.
I think the phrase greed seems a little incorrect. It's more like safe or something like that.
Yeah, because you're right. Because in that scenario, you're in the real world, the real situation in game theory, secure, right? The casino has their vested interests. You as a player have your vested interests. How those two interact is a very complicated dance. In this scenario, I'm just creating a fantasy land of an imaginary bank of slots. Okay. And I want to see if I can figure out the odds. Not me, I know the odds. If the bot can figure out the odds based on just exploring.
Yeah.
So the goal for this is actually to see how closely do I match. Does the bot come back with actual chart match with the actual odds? Does that make sense?
Yeah. One of the nice things that they do in the class is they talk about clinical trials and various patients that have a condition and applying various treatments, whether it's a pill or whatnot. If you gave somebody a pill right out of the hopper and they died, you'd say, well, I'm not going to give anybody that pill.
Right.
You'd find another pill and say, oh, this one actually works. And you start to exploit that good pill. But what you might not realize is going back and like, that death was an anomaly. And that first pill actually might have a better end result if you did enough Monte Carlo with it.
But that's what statistics are for. We don't have like a lot of statistics here.
Well, clinical trials are about statistics.
Yeah, but in that case, it might make sense if you got 1,000 trials to just say, let's do 10 of each, right? 10 trials on each.
There's your strategy, though. There's your strategy.
And then see, how close we get to the true mean of the payout, and then choose some of the higher ones and explore that.
But think about it. If you said do 10 of each one,
yeah,
and then one of them, let's say you got no payout out of 8 of them.
Yeah.
And the other one you got to pay out every time out of 8 of them. If you want to make money, would you still do those 2 more on that one that you got no payout on, or would you just stick with the one that's working?
Right.
I mean, at what point do you say, I tried it enough, this one I know works, I'm just thinking about the one that works.
There is I don't know off the top of my head, but there is a real statistical definition for how you would do that to maximize your stuff. And how many times your sample, you do a sample mean and it will come, how close it will come to your population mean, So in that case, I guess it's just like he's saying it, it's like a contrived example for this kind of understanding.
Right. So maybe if I run through the numbers, maybe it'll make sense. I have no idea why the thing is playing process. All right, so this is the actual odds. This is the ground truth, right? So the fourth one,
85%.
Index 3 is the highest one, right? Second place would be 0, et cetera, et cetera. 4 is not even a thing. We look at what it learned. It learned pretty much the same thing, right? And this is of 10%, which is the part of the upper end of the ideal. So what it learned, just by experimentation, it did a pretty good job. So using the example of pills, this did a pretty good example of figuring out which one had the best success. What's interesting is this actually is a negative number, which means the payoff rate's so low that the bot thinks that it's a negative payoff, right? If this is wrong because it made it 0. So this is basically, and if you rerun this, you'll get slightly different things. Basically, what happened here was, this one probably came up randomly at first. Oh, that's not a reward. Let me pick another one, and then this one. And then when it finally found one that paid off, it stacked and stacked and stacked and stacked and stacked on top of it. And it stayed there. So it picked, index 2, which is not anywhere near the best option. So that's being fully greedy, and you'll see that if you're fully explorative, well, you kind of get the same thing as being 10%, but there is one difference. Anyone want to take a guess at what the difference is? The reward is different, right? So this is 3,609 for always exploring, and with the optimal count, it's 7,800. And it always runs about 8 to 10 times the amount. So the cool thing on this is to run it again and again and again. And it'll show up slightly differently. Let's say,
Oh, because you don't have any.
I'm not doing any.
You don't have any negative switches.
Right. Right. And but run it again, and we see. Right. So yeah, basically it hit and stayed there. Right. And there are times when is it greedy or is it playing it safe? That's kind of a phrasing thing. But what's really cool is you can amp it up now. Number of slot machines. Right, so that's what this looks like. And
so the 10 and the -1 payoff that you put in there,
yeah.
Is that your is that kind of something you're putting on top of the model, or is that adjustable? I mean, obviously it's adjustable, but why did you chose those numbers for a reason, or just kind of?
No, just they seem like
Okay.
Is 10 considered your reinforcement amount?
Right, 10 would be the reinforcement amount. So I mean, the thinking was
would be the opposite, the decrement or
the punishment, I guess.
punishment amount.
So there's I maybe I missed it. When you get to, is it saying that when you get to the 0 is when you move, or just
Zero, when your epsilon is 0, if your epsilon is 0, you are never going to explore.
I know that part, but I'm saying the payoff of 10 and -1.
Right.
So let's say first round, I'm on the 0 bar, which is like a 20% payout.
Right.
And if I 1 out of 5 chance, if I hit it, I get 10 points. If I don't hit it, I get -1 point. Right.
Right.
That has no effect on whether or not I go over to the next bar.
In this algorithm, it doesn't. Because basically what happens is, so let's say I'm going through this completely greedy, right? Remember the argmax, the real thinking here, if you want to call it that, is the argmax, which picks the highest value, right? That's how I'm picking, right? So in this case, okay, well that's having a seizure. Let's let it draw it out.
Or read them.
Yeah, somebody here is going to have a seizure when we see. All right, so there's basically epsilon is the threshold, right? Is that the question? And then you're wondering, well, so if some random number is greater than epsilon, then whole best machine, right? Otherwise, try a new machine at random. Right? So if this is like, I'm never going to do this at all, I'm never going to explore, I'm always going to find the best machine, right? And remember, it's not the best machine in the real world or in the simulation. It's the best machine the algorithm knows about. So if given these 5 slot machines, right? Let's just look at this, right? The first one was like 24%, right? Or 10%. It doesn't matter. Right? So if I win, yay, that's the best one. All right, next time comes around, remember, I'm not exploring, pretty much always going to do this. Right? What's the best one I got so far? 0, 1. Again. Now, the only reason you see the other pattern is what if you pull this one, right? And you don't win. So that's going to have a negative number, right? And remember, they all start off at 0. So, all right, well, give me the best machine. Certainly not going to be this one.
Why not, though? It could be that all the
We don't know that yet.
more negative.
We don't know yet.
But we don't know that much at least.
Well, so what will happen is if they are more negative, eventually we'll learn that, and we'll eventually find the least negative one, right?
But that depends on your epsilons. So.
Totally depends on that example was assuming a completely greedy epsilon. 0. No expiration.
Yeah, so it just stays with the one that it hits first.
Whatever it wins first. It's like my grandmother when she went to Atlantic City. She found a machine that would fade her off. She used that for like 2 or 3 years. Like,
Do people build in changes to their epsilon automatically as part of this learning as well?
yes. So there's a whole thing. Remember what I said that kids are more, I think somebody was talking about kids are more exploratory? Because kids don't have a complete map of the world as adults. And there's also the fact that as you get older, maybe climbing Mount Kilimanjaro, maybe that's not my thing because I'm a wife, I have kids, I have a mortgage. You know what I mean? Like, so if you have a limited map of the world, whether you're a child, whether you're a dog, or whether you're a bot, you don't know, so you don't have anything to lose with it. It's only when you start accumulating something to lose that flexibility and ability to explore.
Assuming people build in all sorts of mechanisms. Like,
There's all sorts of mechanisms.
Number of tests, like fewer tests means, more exploratory.
Exactly. So what you'll see is there's a whole thing. There's a really good book by Pat. It basically goes through all the popular algorithms. There's about half a dozen in the book. It's probably about almost a dozen now. And by the time we get home tonight, there'll probably be 30. But the point is that there's multiple ways to kind of to approach it. Right? And a lot of this is game theory, right? Like, well, you thought of ways to, and you have to be very careful about the scenario you set up. That's why there's another one, the ice field, is even more contrived, right? And it's even simpler. I can show you an animation of it, actually.
Interesting thing is, I think there's no right answer. I mean, I look at this and think to myself, my wife is more likely to find something and stick with it, where I'm willing to try different foods, even if I know I like spaghetti, I'll try different foods,
Right.
And somebody else would, and that doesn't mean she's right or doesn't mean I'm right. It's just that everybody's going to be a little different. All the algorithms can be different depending on what type of person you want to portray.
I think one of the key takeaways is when you look at the rubric for the coursework, what Frank's discussing now is like chapter 1. It's kind of setting
Right. It goes.
So everything you're discussing is all these other more sophisticated algorithms that you learn in the rest of the course address all the questions you're asking.
Right. So this is basically a video of a representation of, right, this is navigating the ice field, right? So S stands for start, G stands for goal.
Why do you say navigating ice field? I'm sorry, what is
So this would have been the next demo, right? So basically you play a little bot that's trying to safely navigate.
It's like trying to walk across a
trying to cross an ice field. Frozen lake, that's what it is.
Yeah, frozen lake.
And it kind of what it's basically doing is it's going and it's, I mean,
S is safe.
S is the start point. F is a safe place, like a free place to stand. H is a hole, so you fall in the ice. So what it's doing is it's learning where not to go.
Oh, I see.
So basically, and it's in the article, right, and this month, right, and my tech reviewer's in the back. So basically, if you did this at random, and it was just kind of an academic exercise, very chapter 1 type stuff, is that 1% of the time, it would find a way at random, right? So basically what happens is that when if it runs into the edge, to a hole, it dies, right? So, and it's basically, you want to constrain the environment that you're doing simpler, for a simple RL problem, right? Because if it were easy, self-driving cars would have been out 20 years ago. Right? You have a lot of things, a lot of independent systems that kind of have to work together. So I'm going to work through the rest of the slide deck, mostly because I have a lot of Git animations, right? So one way to approach this, how I solve this algorithmically, is using what's called a Q table, right? And Q, I've heard, stands for quality. It can also be the German word for Quelle, which means source. But basically, it points out that memory plays an important role in learning. If I were to run the simulation, about 1% of the time, the little bot finds its way across the frozen lake. By implementing a very basic Q table, it makes it half the time. Still wouldn't want to be that little bot driving my little snowmobile over the lake, but still, it has a better check. So basically, it's basically try and fail, and it remembers where it failed. And that is pretty much that's why we have memories, right? That's why we evolved to have memories, is to remember when we messed up and when we were successful, right? And then the guys from Mythbusters, they say it's just playing around once you write it down. Once you write it down, even if you're playing around, it's science, because you're taking notes of what happened. All right. So what's really interesting, and where most of this cutting edge stuff is being done, is on Wall Street. And there's a really good video by Siraj Val, I'll put it in a link in the notes, where he kind of goes through this. Basically, the first person to apply analytics, and we're not talking robots and stuff or AI, we're just talking basic stats from real-time data, was Michael Bloomberg. He ended up pretty well for himself, I would say, right? And when I worked on Wall Street in the 90s, it was, you knew who the important guy or gal on the floor was, but who had a Bloomberg terminal, right? So when I was doing tech support there, I knew if the person had a Bloomberg on his desk, I'd best make sure I fix their machine first, right? Everyone else can wait, right? Which I guess in itself is kind of an RL algorithm. What's cool about this is that, some of this more advanced stuff, right? The big problem that the kids have with math is it doesn't apply to the real world. This is like straight up real world stuff, right? So we saw that the SEC authorized electronic exchanges in the 90s. How many people remember hearing about the flash crash? Right? So basically the stock, I forget what it was, but it basically, something triggered. And yeah, so the stock market crashed by a couple hundred points in like 20 minutes and then went straight back up. Which, I don't know if the results of the investigation were ever made public, but the real key to take away is just imagine what these folks are doing, because they've been using AI as quants, as they were called, for a long time. And one of the key structures here is this notion of a Markov chain. And there's a Markov process where basically it kind of completes a full circle back. Does that make sense? So this is if you have a Markov chain, you would use or not use certain algorithms based on that. And since we're talking chains, I had to bring up this. But basically, this is kind of what he goes through in the video, where he talks about, state. You have state, you have agent. P or pi stands for policy. And I have a policy that if a certain stock drops by so much in one day, if I own it, I'm going to dump it. If I don't own it, I'm going to buy it. And that's a policy, right? And these are kind of rules. So again, with that chapter 1 analogy, policy is kind of like chapter 2 or 3, right? Because then you can kind of stack these things, right? So if I can have more advanced ways to solve the whole bandit problem. And then basically, you have 3 actions, right? You can buy, you can sell, or you can hold, and that becomes 3 to the power of n, n being the number of stocks in the portfolio. So if I have 1,000 stocks, 3 to the power of 1,000, these numbers get big pretty quickly. And that dovetails nicely into your computer vision stuff, which these numbers can get big pretty quickly. And what is important about why GPUs are suddenly become something that only like hardcore PC gamers have cared about, to now crypto people and data people really want it, because you're doing lots of math in parallel. And that's really what makes GPU really good at this. So the reward would be, how much money you made on it, your current. So you'll see, and he walks through it really well in the video. So I can't sign into the thing, and it works about 100% of the time, works 80% of the time. Right?
Which video are you talking about?
This is Siraj Raval.
Oh, Siraj's video.
Siraj Raval is a force of nature. Pretty awesome guy. He's really good at explaining stuff. He's really into the special effects. But like you'll see, like he talks about this, and the code for this is on GitHub. You can download and play along with it. It's pretty interesting to think about that. What's really cool is we can pull the historical data. So this bot thing would go through and pull through 16 years of stock data.
Just a comment, the #1 category competition that's out there right now is to do stock predictions based on news feeds.
Interesting.
I know. It's $100,000 and stuff. That was interesting.
See, that's what's really cool, because then you can tie in sentiment analysis, right? So is this a positive or negative story about a company? And
everybody's doing it based on stock prices, and that's going to be news for a long time. Doing it on news feeds is going to be new.
Doing what basically?
It's analyzing the news feeds and trying to project future stock prices.
Oh, but what was it before?
They just look at old stock prices.
just stock prices. So IBM, it's the kind of thing where IBM will always go up in October. Right? I don't know if that's true. Don't that'd be like Frank said. I knew this was the case for Toys R Us. They're dead, so you can't buy them anymore. Every October to November, their stock went up, and then every January, okay. So kind of do the same thing works for currency trading too.
A lot of them, the Dell stock would go up, and then a week later, the guy who makes the Dell chips would go up. So there's these patterns like that.
Right.
So there's different stocks.
So if you had visibility of the supply chain, that would be something you would know.
Right, exactly. You can see if I look at the patterns of all the stocks.
Right, exactly. So this is the code where you basically see, and you'll see a lot of these concepts kind of, go here. Epsilon minimum. Somebody asked, will you change epsilon over time? Epsilon decay. You did two guesses to see what that is, right? Epsilon would decay over time, and now that changes things. So there's a lot to this. So I find it fascinating. I find it extremely frustrating too, because I hated math as a kid, and I love math to a point, but this really goes beyond the frontier. But this is going to be the next hotness, seriously.
RL?
Oh yeah. Because now everybody and their cousin is they do YouTube videos, and they have there's courseware on data science this, data science that. This is going to be I would say the next frontier, but where the frontier is pretty far out already. So this and transfer learning, I think, is going to be hot. And transfer learning is how the custom vision service works. You can play with that. Basically, you train a model to 80% of what it should be, and then you feed a little bit of extra data, and then it's ready. The advantage of that is that if you're the person that uses a almost baked, it's like buying a frozen pie, right?
Oh.
Somebody already did most of the work. You just have to finish it.
Right. Oh, wow.
Right? So that's why you can come up with a pretty effective custom vision demo, or computer vision demo.
80% of the way there.
Right. So all I have to do is feed it 30 images, and it can tell if a train track is broken or not with about 80–90% which is not bad for 15 minutes of work on my part. Somebody else did all the hard work. Like from great user broken pond. Cool. Think amount of time. That's transferable. But this is cool because it really ties into a lot of real world stuff. If you have kids or have pets, you can kind of be like, oh yeah, I know what he's doing. He's to everyone else, it just looks like he's in the middle of like, you know, bug rockers jumping up and down on a table. But he's learning his boundaries, which apparently they exist yet.
So you said this was a tough RL, tough EDX class, right?
It is.
And I actually happened to take in the degree thing.
Right.
So I've taken a bunch of EDX classes. What would you say is a really good, like the AI one, or what do you think is a good
Oh, they're all
EDX
good.
class?
They're all good.
What would be like the next one you would take after standard data science?
So I actually did the data engineer one,
Okay.
which I thought was good. Because what I found was, and when I was doing the data science thing, the cool thing about the data science program is it opens up a lot of opportunities. You know a lot, but it doesn't really talk about. Well, they don't mention Hadoop, they don't mention Hive, right? Like, how could you, when you go to a real world project, you have to have some familiarity. The data engineer one goes through that in depth. And right, am I right, Andy?
Yep.
Because we both did that one together.
Is that different than the professional program for big data? Or
Yeah, it's called big data, but it's really data engineering.
Yeah, I call it data engineering.
Oh, it's
Yeah.
called big data, but it's the same thing?
Yeah.
Same thing?
Yeah.
It covers the platform technology.
All the platforms, you know,
It's actually pretty easy.
Azure Data Factory.
It's great.
Hadoop, Hive, Spark. It also covers how to deal with real-time data.
But how about for machine, let's see, that's all.
The machine learning one, I have 9 courses in, and the RL one is course number 9.
Oh, so you're working on capstone too?
I'm gonna get the 3rd one, yeah.
Yeah.
So it'll be like
So what, which one is it, machine learning is it called? or-
AI.
machine learning engineer one.
It's
There's one that's a professional program for big data, that's machine learning. Then there's the data science one you already did, which is statistical data analysis. Then there's AI, which covers ethics and math and a bunch of stuff.
Right, so was
including
the
RL.
AI one, did you do that one yet? or
I'm
not?
9 out of 10 courses through.
Oh, that's the one that has this RL in there.
RL is class number 9.
So we're going
So-
through the capstone.
Work up to it.
You're working on the capstone
Yeah.
now, capstone?
Work up to it. Like, don't start at
I-
that.
It takes a long time.
But I mean, it's hard because there's just a lot of things at play, and the more complicated your simulation is, the more complicated your process.
The AI, so the AI.
One of the
Coursework
problems
is
that I
a good
would
one.
criticize is they have a guy named Graham Malcolm.
He's
who's
awesome.
really articulate and awesome.
Uh-huh.
For these, they get the goober geeks from the research and development department, and they're all like, you're smarter than that, but you can't communicate with them.
Uh,
So that's the problem.
I'll tell you what I discovered though is if you want to learn the math stuff,